Recap on the theory of reaction rates. For a chemical reaction to occur, reactants molecules must approach each other. They must pass over an energy barrier. Spaces at the top of the barrier are called activated complexes. According to Eyring, Eyring, and Polanyi, it can be assumed that the activated complexes are at equilibrium with reactants, just like we said before. The concentration of reactants, products, and activated complexes can be calculated accurately by statistical mechanic methods. Even when reactants and products are not in equilibrium, the activated complexes are at equilibrium with the reactants. For instance, A plus B at equilibrium with X double dagger, which is at equilibrium with C plus D. If C and D are withdrawn immediately, it is assumed that this does not affect the equilibrium forwards. Derivation of the concentration of activated complex. If equilibrium is assumed, the concentration of the activated complex is given by, as looked at before, X double dagger is equal to A times B times QX double dagger, QA over QA, QB times e to the minus e naught over RT, where X double dagger is the concentration of the activated complex moving in both directions, i.e. left to right and right to left on the first equilibrium. So that the concentration of that is actually 2 times the complex left to right. Factorize the Qs into various kinds of energy. Assume A contains 3 n atoms, hence 3na degrees of freedom. That is, Q is equal to a product of 3na factors, of which 3 are translational, 3 or 2 are rotational, 3na minus 6 or 3na minus 5 if linear are vibrational. The above is also true for X double dagger for Na plus Nb atoms. Na plus Nb atoms will be 3 into Na plus Nb minus 6 vibrational factors if nonlinear. One of these vibrational factors is of unique character. It corresponds to very loose vibration or vibration to translation transformation, which allows the complex to dissociate products. For this one, vibrational degree of freedom, let us replace it by its factor, by a value of its function calculated in the limit at which the frequency tends to 0. We do this by expanding an exponential function and taking only the first term. So the limit as nu tends to 0 is equal to 1 over 1 minus e to the minus h nu over kt, which becomes 1 over 1 minus h nu over kt, which is equal to kt over h nu. We now express the equilibrium constant K, including Kt over h nu. Replace Q x double dagger by Q double dagger, because we have removed one frequency, which now refers only to 3 into Na plus Nb minus 7 degrees of freedom of vibration, or for a linear molecule or a linear complex, 3 into Na plus Nb minus 6. Let's now look at the concentration of the activated complex. Note that Q x double dagger is equal to Kt over h nu Q double dagger. Hence, the concentration of X double dagger is given by X double dagger is equal to the concentration of A times the concentration of B times Kt over h nu times Q double dagger over Qa times Qb, all into e to the minus e naught over RT. Let us rearrange this to obtain mu times the concentration of X double dagger is equal to the concentration of A times the concentration of B times KT over H times, open bracket, Q double dagger over QA times QB into e to the minus E naught over RT. Here, nu equals the frequency of vibration of the activated complex in the degrees of freedom corresponding to the decomposition. Hence, nu times the concentration of X double dagger is equal or corresponds to the rate or the velocity of the reaction. This, of course, is referring to left to right. But we are already aware that when we talk about velocity of reaction, V is equal to a rate constant Kr times the concentration of A times the concentration of B. And we know then this is equal to nu times the concentration of X double dagger. Consequently, rate constant is given by Kr is equal to Kt over H, Q double dagger over Qa times Qb, all into e to the minus E naught over RT. This equation applies to bimolecular reactions, i.e. the activated molecule is made up of two molecules A and B only. So the rate is proportional to A times B, i.e. one of A and one of B. For n molecules, the rate is proportional to the product of n concentrations. Here now, molecularity is equal to the number of reactant molecules that occur in X double dagger the complex. And Kt over H has units of per second, i.e. is a frequency. And at 300 K, Kt over H is approximately equal to 6 times 10 to the 12. The basic equation derived above for absolute rate theory should reduce to kinetic theory equation if 1. Reacting species have no rotational or vibrational degrees of freedom. 2. Only possible for reactions between two atoms. For this case of reaction between two structureless particles, the rate constant is Kr is equal to Kt over H, Qtx double dagger, Qrx double dagger, all over Qta times Qtb, all multiplied by e to the minus E naught over RT, which when you put in the translational, you obtain Qtx is given by that. Okay, Qtr is given by that. Then the others is given by this and that. Here I, of course, is equal to MA MB over MA plus MB D squared AB, where D is the distance between A and B. No vibrational partition function must be included for the activation state since the atomic species has only one vibration, degrees of freedom, and it is represented by Kt over H. Cancellation of common terms reduces the expression to Kr is equal to D squared AB into 8 pi Kt into MA plus MB over MA times MB, all to 1/2 e to the minus E naught over RT. This is identical with the expression derived using kinetic theory of gases in the collision theory. However, when reactions between molecules are considered, no agreement is found between the two methods. Reactions between molecules. For A and B is simple, we can calculate partition functions, hence we can get quantitative values for Kr and hence rate. For generalized systems, it is best to use transition state theory to obtain an appropriate, in order of magnitude, an appropriate of factors that influence the rate of an elementary reaction state. We use the appropriate values of partition functions. These do not vary much with the masses of molecules or with moments of inertia. Apply these values to species in A plus B to give you a B, where A and B are polyatomic molecules containing Na and Nb atoms and are nonlinear. AB star is nonlinear. Hence, each has 3 rotational degrees of freedom, 3 translational degrees of freedom, etc., as seen before. So QA is going to be equal to QT cubed, QR cubed, QV3n minus 6. QB is going to be QT cubed, QR cubed, QV3n minus 6, and Q double dagger is going to be QT cubed, QR cubed, QV3n minus 6. But KR is equal to KT over H into Q double dagger over QA QB into e to the minus e naught over RT. Substitute for the various partition function gives KR TST is equal to KT over H into Q to the 5V over Q to the 3T, Q to the 3R, all into e to the minus e naught over RT. Remember, QV is equal to 1, QR is equal to a value of 10 to 100, QT is equal to 10 to the 8, 10 to the 9, which implies KR is going to be of the order of 10 to the minus 15 to 10 to the minus 14. From collision theory and following the rigid sphere model, we have QA is equal to QT cubed, QB is equal to QT cubed, and Q double dagger is equal to QT cubed QR squared linear. Hence, QCT is equal to KT over H, QR squared over QT cubed, e to the minus e naught over RT. So KRTST over KRCT is equal to QV over QR all to the 5, which is approximately equal to P. Since QR is greater than QV, it means P is very, very much less than 1. i.e. reactions between polyatomic molecules are slower than expected on the rigid sphere model. This is because several rotational degrees of freedom are lost and replaced by vibrational degrees of freedom, which have smaller probability associated with them. KR decreases with A and B getting complex. P also decreases with complexity of molecule. The pre-exponential temperature dependence decreases into negative values. Disadvantages of TST. 1. The assumption of equilibrium, that the equilibrium of that of X double dagger is maintained, is a bit tricky. Consider the instance. A plus B, first equilibrium, K1, K minus 1 to give you X plus. Second equilibrium to give you AB double dagger. And finally by K3 to give you products. X plus can be called the energized molecule, and AB double dagger can be called the activated complex. If K minus 1, K prime minus 1 are greater than K2, the equilibrium of X won't be maintained. Hence, we must know the difference between activated molecules and activated complex. That means A plus B, K1, activated, K2, activated to give you products. The first one is activated molecule, the second one is activated complex. For unimolecular reactions at low pressure, TST cannot be applied because the collision probability will be very low. Collision theory cannot be applied to unimolecular reactions because collision must involve at least